Let me check on YouTube. Okay, YouTube is fine. Perfect. So please start.
Okay, thanks to everybody, and I welcome everybody to this second part of today's workshop. So I want to spend a few words to thank Yuri and Gianluca for the excellent work during this meeting. Let me introduce the first speaker of today, Till Hartmann, and he's going to talk about alignment-free detection of copy number variation using strongly unique kernels and fused lasso regulation. Thanks, Till, for attending the meeting. Please, you can start.
Yeah, thanks for the introduction. Thank you for having me. So, as you already heard, this talk is about alignment-free detection of copy number variations using strongly unique k-mers and fused lasso regularization. So let's first recapitulate what copy number variations are and why we want to look at them. And when you have a, say, a chromosome, a human chromosome or something, some sequence, you may encounter segments that get duplicated, and then you see something twice or 3 times or 4 times, or not at all. You may even have losses or deletions. So you kind of want to know if there are any of these large events or not. And these can, of course, influence gene expression and are very common in cancer cells. And we get a lot of these cancer cells in our group for analysis questions. So yeah, just to give a quick overview of copy numbers. So why do we want to do it alignment-free? So in most cases, alignment-free approaches are way more efficient than mapping-based because we save computation time when it comes to mapping. We save storage space of all the BAM files or CRAM files you need to store. So it's just a way to try to save resources and be probably faster. We also tend to avoid the mapping bias that is introduced during the mapping step. And which is the nicest part about this talk, I guess, no, perhaps not, perhaps, is that since we're counting k-mers, we can give a direct copy number estimate as long as the k-mer is unique in the genome. So we get absolute copy numbers from whole genome sequencing data, for example. This is just an example. We have some sequences as input. These are raw reads, and we put them to through our pipeline. And what we get is the typical copy number variation plots. Since this is a human sample, we expect a deployed sample. We expect the copy number to be about 2. Since this is a cancer cell, we expect it to be wildly going up and down, which is also doing. So that's fine. Yeah, so let's have a look at how we do it. And first, we try to define, we actually define robust k-mer probes, which are strongly unique k-mers, so that aren't only unique in the genome, in the reference genome, but also have no Hamming distance 1 neighbors in the genome. So we can avoid some of the sequencing errors and better place them. Right. So if we have this reference, the reference file, we can then, for each position, put a bit if it's a strong k-mer, strongly unique k-mer at that position or not. And then we get a bit vector of zeros and ones that is very small to save. So it's only 350 megabytes or so in the end. And once we have that bit vector, we can just take a sample, deduplicate all the raw reads that we have, just using a Bloom filter in a streaming fashion, then count the actual k-mers. And here you can choose any k-mer counter that you like. we chose KMC. We will come back later to that. And then we still need to convert the counts, since these are just Kmer counts, to copy numbers. And to do that, we look at the Kmer count histogram. Then we can finally assign the copy numbers to the positions in the genome. So we term this in the terms of measuring the copy number signal on the robust probes across reference, because that is usually the terms used for array data. And once we have that signal, we can define segments where the copy number doesn't change using fused lasso. So part 1, how to choose these strongly unique Kmer probes. How do we do that? First of all, we need unique Kmers. And for that, we use the three-way bucketed cuckoo hashing approach, where you have for each, you have 3 hash functions, and each of these hash functions maps a Kmer to hopefully to a different bucket. So a bucket then has up to 4 elements, which can be stored there such that they fit within a cache line. So that when you try to query a Kmer, you look at the first hash function, and if you find it in the bucket, you're good. If it isn't in there, you have to check the next hash function, and that incurs a cache miss, which you want to avoid. But we find that mostly it's just one cache miss in average, or 2 perhaps, depending on the load factor. So with this hash table, we can just count, because we can mark if the Kmer has already occurred. So if it's has been seen once or more than once. So we need just 1 bit for that. And to save some more space, we don't store the actual complete keys, but only parts of the keys, since we can recover them using the quotienting approach. So we save the first few bits of the key and the hash function that was used to store the key. Right, so now we have unique Kmers and non-unique Kmers in our hash table. And then we still need to find the unique ones that have no Hamming distance 1 neighbors. And a naive way to do that would be just take a Kmer and look up each of its 3K neighbors, and mark a Kmer as weak if any neighbor, if it has any neighbor of Hamming distance 1. But that can take quite a while, so we don't do that. Instead, we take the list of Kmers and also their reverse complements, and we just sort it, just regular sort in place. Then partition this into blocks by a prefix, Kmer prefix of length k divided by 2. So just a prefix, a middle, and a suffix. And then we have disjunct blocks of Kmers, and we only need to test for Hamming distance 1 inside of each block. And this check can be done using some bit magic, just basically some logical ANDs, ORs, and XORs, to test if 2 suffixes are the same or have a Hamming distance of 1 or more. No, whatever. So the blocks themselves can, of course, be processed in parallel, so we don't need to do this sequentially. So now we have a hash table with unique Kmers or non-unique Kmers, and we can mark the unique Kmers as weak or strong. And with the strong ones, we can have a look at how the numbers of strongly unique Kmers is rises with the choice of k. So as expected, the larger the k, the more strongly unique Kmers we see, and also the less weakly unique Kmers we see. Note that the amount of non-unique Kmers in red is pretty low, but that's of course because non-unique k-mers appear more than once. So if we actually look at the positions that are non-unique, we get way more than that. So we chose to do to pick k equals to 27 because we don't gain much from 29 apart from increased memory consumption later on. Also, if we look at the build times for the table, we can see that the wall clock time is actually pretty much the same for all k, and that the insert time is pretty low, but rises with k as k goes up. On the other hand, the time for construction is mostly spent in marking weak k-mers. So yeah, that is something we would like to address as well to make that a bit faster. Now, what's actually interesting is if you look at the gaps between strongly unique k-mers. And what we see here is a cumulative distribution of the gaps, where both axes are logarithmically scaled. And most of the 27 strongly unique k-mers are adjacent. So they have a gap of 1. And there are some that have a gap of 2, and it quickly dwindles after that. So remember, this is twice log scaled. So there are a few gaps that are large, like larger than 10k. So you can see the numbers here, so I won't read them now. And there's also gaps that are really large, like the maximum gap is about 400,000 in the reference genome, and that is probably caused by exact repeats in the genome. So we can't do much about that at this point. But however, if you were to align the reads instead of using an alignment-free approach such as this, you would have the same problems with placing the repeated sequences. Yeah, so moving on, part 2. Actually calling the copy numbers in whole genome sequencing samples using those probes we defined before. First of all, we take the sample and deduplicate the reads. We did that just using a large Bloom filter. I already talked about that. And then we used KMC3 to count the actual k-mers to get the usual k-mer count database. And we used specifically KMC3 because it has a C++ API which we can access from Rust. So once we have that, we need to assign the counts to genomic positions. And how we do that is we do take the bit vector we defined earlier of strong k-mers in the reference. So remember, there's a 1 at that position if at that position in the reference a strongly unique k-mer starts. And then we just iterate over the reference and the bit vector together, query the KMC database, and have a position by count signal here, just as depicted. Now we still have raw counts, but we really want to have copy numbers, not counts. So what we do is we take a look at the count histogram or k-mer spectrum sometimes called, and we find a count that corresponds to copy number 2 because we are actually at the moment only looking for deployed genomes. And for low coverage data, we do not have that left tail that you've seen in previous talks because the coverage is so low. So there's a lot of information missing. And we also have the erroneous 1 counts in there. So what we do is we try to fit a polynomial, a quadratic polynomial locally around the mode, so somewhere around 6, and use that as an estimate for a normative count. Or if we have high coverage data, we can fit a negative binomial mixture model using just expectation maximization approaches. And then we have something that we call a copy number in this respect. So finally, the segmentation step. We have chosen to do the fused lasso approach instead of the often done circular binary segmentation. And fused lasso is defined as follows. We have an objective function f of x, and we want to find a minimizer x such that x is close to our signal y. These are the blue points, and we want to find an x that is close to y in the sense that the square differences are small. But we also have a penalty term that restricts neighboring x values to be close together. Yeah, so in this case, we want this to perhaps might look like this. So depending on the choice of lambda, we can get a segmentation that looks like this, or rather an approximation of y that looks like this. Now the approximation depends highly on the choice of lambda. We chose to define lambda in terms of some constant lambda divided by the distance between the strongly unique k-mers in the genome. So most of them have gap 1, so this is usually just constant lambda 0 divided by 1. But some of them, as we've seen, have a gap size of 10,000, so we don't really want to bring values together or equalize values that are far apart, but rather those that are close together in the position terms. However, if we choose lambda 0 that is too high, we might only get one segment like this. And this is still something we are looking into, like how to choose the parameterization for fused lasso. And one idea is to estimate the lambda 0 as the largest lambda such that we only get one segment, and then we know, okay, this is the largest lambda we may choose to just get one segment, and we can iteratively adapt this to smaller values depending on what size of copy number segments we are expecting. So in the range of 1 megabase or a kilobase or whatever. Yeah, this is something we are still looking into. This is all work in progress. Here's some results for cancer cell lines. This is pancreatic adenocarcinoma. We have 2 low coverage whole genome sequencing samples and one higher coverage whole genome sequencing sample, which is a normal. So for the normal sample, we expect it to be copy number 2 everywhere. And for the cell lines, we know that there must be some losses and gains. So here are some plots. I hope these are at least somewhat colorblind safe. So the bottom one is mostly yellow, and this is the normal sample. And yellow in this case means copy number 2. So this is exactly what we wanted to see. Great. For the cell lines, we can see there are some red regions which correspond to losses, or green regions which correspond to gains. And then we've also a black region which is a complete deletion in chromosome 9 in this case. So let's have a look at chromosome 9. These plots are still preliminary, but you can see the loss in the CAPAN1 sample at about 200 million base pairs. And there's also a loss at that position in the other sample, and these are actually related cell lines. I think one is the primary tumor and the other isn't. So it might be of interest to look at the differences between the two, and we can actually do that just by checking the differences. So we get a better picture of how two samples deviate from one another. So this can be quite interesting. So in summary, what did we do? We took raw whole genome sequencing reads and called copy number variations for them, just without mapping and trying to minimize the amount of storage in between the steps, and do that quickly. How? We counted strongly unique k-mers in the sample, and then we can derive a copy number signal along the reference. And for the actual segmentation of the signal, we use fused lasso, and we've seen that it gives quite nice results. But what we do also need to address is, of course, that copy numbers usually are discrete in integers if we don't have subclonal things going on. But so they should be 2 or 1 or 3 or 0, not 2.3, 3, 3, 1, 7, whatever. Why did we choose to do it that way? We wanted to avoid read mapping and alignment, just to save on resources. So energy, CPU hours, memory usage, storage space, and so on. What we still think might help is to include more k-mers that are known to be variant, like frequent variants. So perhaps alternate alleles or common SNPs in general. Then we would have to change the step on how to find unique k-mers a bit. Then we can probably easily speed up the weak k-mer detection a bit. Also, we are currently using the KMC and count all k-mers of the sample, when actually at the moment we only need the strongly unique k-mers, so we're doing more work than needed. And as we've seen in previous talks, there are ways to properly count only a specific set of k-mers faster. So maybe we can have a talk about that later. Yeah, and then what we really need to do is find proper fused lasso parameters and do actual evaluation on larger datasets. Yeah, and possibly compare with other tools.
Thanks. Thanks, Till. Okay, thanks for the talk. Let me see if there are any questions. Okay, I see something here. Okay, let's start from this one. Do you consider the prediction as final, ready for medical use, or do you have to reanalyze the samples with mapping-based approaches to convince medical staff?
No, we don't consider. This is still work in progress. We started this like 2.5 weeks ago or so. So what I can say is that we usually work with researchers in the medicinal world, and they are fine with these results since we can answer their questions. And I don't think, we really want to avoid mapping, and we can do that. And I think, of course, for the evaluation, we will have to map and check with other results to see if our results are accurate enough for medical purposes.
Okay, thanks. There is another question. How much do the results depend on the reference used to generate the strongly unique k-mers? And if you have compared these to tools such as Expansion Enter, De Novo, or FlexTyper? And there is a further question. Does removing duplicates in the reads affect of the copy number? So maybe you can see the question.
Okay. So we haven't done much work yet on different references used, but what we did use, do I have this here? So we used the analysis set from UCSC as a reference. We also, in a previous version, used the NCBI version of some analysis set, and they already disagree a bit. But we try to incorporate some unplaced scaffolds and random sequences and EVV, so we get more robust k-mers that way. Regarding the deduplication, I can't answer that. I haven't looked into that yet.
Okay, so there is another one, and I think it's related to the fact that you may have copy number variation in the sample genomes, and of course the question is if you can call variation in this case since k-mers are not unique. So basically the question is when you are not able to detect variations, copy number variation with the method.
Well, the genome. Okay, I see. If you use a reference that has a duplication, for example.
Yes, exactly.
Yes, then
not unique k-mers, of course, at that point.
Exactly. Then you have no unique k-mers at these positions, but you could mask the duplication in the reference if you know there is one. That is a way to solve that, I guess.
Okay, since maybe I will ask you just a last one very fast. What about the choice of the K in your method? Can you say something about the K, the use of the K? How it changes the results?
Not very much, as we can see from this one. We get some more probes, some more strongly unique k-mers, but it doesn't really change much. Maybe we get slightly fewer large gaps or so, but I doubt that. I don't think. Okay.
Thanks, Till. So thanks again. Thank you again
very much
for answering questions. And let me try to see if I can see the next speaker, Paul. Yes. So I can see you. Can you share the screen at this point?
How's that?
Okay. Yes.
Okay.
I can see. Okay, so Paul is giving a talk on the statistic of k-mers from a sequence undergoing a simple mutation process without spurious matches. Thanks, Paul, for the talk, for giving this talk, and please, you can start.
All right, thanks. So this is joint work with Antonio Blanca, Robert Harris, and David Kozlicki. We're all at Penn State University, and this is based on a paper that will appear in Recom, but is already available in bioRxiv. So in this talk, I'll first introduce the model, again give a few motivating applications, and then look at the distribution of the number of mutated k-mers in this model, and conclude by providing a confidence interval based on this. We'll then apply this technique to other random variables and get some experimental results. So here's a simple generative model of a pair of genomes. We start with a genome A. We mutate every nucleotide with some probability R1. So here there are 3 mutations that happen, and we get a new genome B. The one assumption we make in this model is that all the k-mers are unique, both in A and in the new B. And this assumption we'll see later on, but in general it tends to be valid when the K is large enough. Now, in this model, we are not observing the nucleotide sequences themselves, but we're observing k-mers. And anytime we're working with de Bruijn graphs or other k-mer-based methods, this is often what's happening. Here I have a convenient way to show all the k-mers that are in this genome with each k-mer being a dot or circle indicating the k-mer starting at that position. So here I'm going to take k equals 3, and so I have every single k-mer, like this is the last k-mer of the genome, and I'm going to observe that each of the nucleotide mutations also affected k other k-mers. So those k-mers also became mutated in this case, and in this case these two nucleotide mutations together jointly affected these 5 k-mers. We can, for example, then observe the number of mutated k-mers. So in this case, that would be 8, and that would be a random variable whose distribution is given by this generative model. But we might observe other things. For example, we might observe the Jacquard similarity between the k-mers of A and the k-mers of B. If you recall, this is just the number of shared k-mers divided by the number of total k-mers. And in this model, where the number of k-mers in both sequences stay the same because we don't have any indels, and the only way to create non-shared k-mers is through mutations. In this model, the Jacquard can be written as L, which is the number of k-mers, minus the number of mutated k-mers, over L plus number of mutated k-mers. We might also observe the min-hash Jacquard. So in this approach, instead of looking at the full k-mer sets of A and B, we first create a min-hash sketch of A and a min-hash sketch of B, and we compute the Jacquard between those min-hash sketches. We call that J hat, and classical results tell us that it's a good estimate of the true Jacquard. So these are just some of the variables that you might observe in this from the simple model. Let me give a couple of motivating applications. The first is the MASH distance. This is a great paper from Ondoff and colleagues in 2016, and it was actually part of Carol's talk already. So here we start with 2 evolutionary related sequences. We observe this J hat, this min-hash Jacquard estimator, from the 2 genomes. And now we assume that the genomes evolved under the simple model which I just presented, and based on that, get an estimate of R1 from J hat. And a point estimate is, of course, really great and useful, but wouldn't it be nicer to have a confidence interval instead? And what that means here is that you're given these 2 sequences that evolved under the simple model, and you've observed some number of mutations. What is an interval that will contain R1 with 95% probability? Now, for example, R1 could be between 0.4 and, or say 0.1 and 0.2 with 95% probability. Here's another application, and this is in several papers in one form or another, where we have alignment of reads to a reference, and the reference is a de Bruijn graph, which means that we're not looking at nucleotide matches, we're looking at k-mer-based matches. In this model, we have that a read is generated from some genome location, and again, we can take this simple model as an approximation of the sequencing error rate that's introduced. But here, the R1 is this sequencing error rate, which usually we know, at least approximately. It's not, like in the previous case, the biological mutation, which we don't know. So here, then, the question becomes different. An aligner wants to either accept or reject the putative genome location as a possible alignment. Okay? And what it does at that location is look at how many k-mers don't match, and that becomes n-mute. Well, yeah, so in this case 8. And we want to accept or reject this alignment with 95% chance of being correct. And in statistical terminology, what we want here is a hypothesis test with significance level 95% for n-mute. In other words, given R1, so we know R1, what is the range into which the observed number of mutations would fall with 95% probability. So it could be if R1 is 3%, then NMUT should lie between 5 and 7 with 95% probability. And in that case, you would reject this alignment. Of course, 95% is just a placeholder. In theory, we're going to use some general alpha in here. So now let's look at the distribution of the number of mutated k-mers, because this is the starting point for any kind of statistical analysis. The expectation of NMUT is easy, and it's done in a lot of papers. This is not new. But let me do it a little formally here. Each of these k-mers we can represent with an indicator random variable xi. That would be the k-mer starting at position I, like here would be x6. And it's 1 if that k-mer is mutated, and it's 0 if that k-mer is not mutated. The expected value of each xi is then just the probability that a k-mer is mutated. And this is 1 minus the probability that it is not mutated, which is the probability that each of the k positions is not mutated. So we have this expression, which we'll use rk as a shorthand for. Now the number of mutated k-mers is just then the sum of these xi's, and if we want the expectation, then by linearity we can move that expectation inside the sum, and we get that it's L times RK. Okay, but let's, and this is where every paper that I'm aware of kind of stops, and here we wanted to go further to understand the distribution. The first thought maybe you have is NMUT a binomial? A binomial is a sum of independent Bernoulli trials, and NMUT is indeed a sum of Bernoulli trials, but these trials are not independent. And the way you can see that is that nearby xi's are dependent. If my neighbor if my xi plus 1 is mutated, that increases the chance that I'm mutated. And this is because the k-mer mutation occur in these clusters. But observe though that far away the xi's will be independent. Okay. So let's capture this dependence with a lemma in the form of the joint. We want to write down the joint probability distribution of xi and xj. Now, if they're far away, then those variables are independent. So the joint is just the sum of the individual probabilities. But if they're nearby, then the joint distribution is given by this formula. And this is not a difficult proof. The way you would do it, here we would visualize the xj as an orange box and xi as a blue box, and you'd break your analysis down into 3 cases. In the first case, you would have at least 1 mutation here. You can compute the probability of that case happening plus the joint probability conditioned on that case, which in this case, a single mutation here guarantees xi is 1 and has no effect on xj. So the joint probability is actually just the probability of xj being 1. In the second case, we have no mutations in this half, but at least 1 mutation here. And we can compute the probability of that case and observe that in that case, both xi and xj are guaranteed to be mutated. So that probability is 1. And in the third case, there's no mutations here, so xi has to be 0, so the joint probability is 0. Now, these 3 cases are a partition of the event space, so applying the law of total probability and Bayes rule, we just multiply each pair together and add them up, and we get our lemma statement. Okay, and if you didn't follow this, don't worry, forget the last 2 minutes happened. Let's just move on. So from this joint probability, we can now easily compute the variance, because the variance is the sum of all these pairs minus the square of the expectation. And when I say easily compute, I mean it took us probably more time than I would admit, because it's sort of tedious algebra and it's very easy to make mistakes. but it is just algebra in the end. Now, once we have the variance and expectation, if this was a binomial, then life would be easy, because the way we would do a hypothesis test or confidence interval for a binomial would be just to approximate it with a normal distribution. But in our case, it's not clear that we can do that because we're not a binomial. However, it turns out because our dependency structure is so localized, we will be able to do it. And this comes back to a definition from 1948 of M-dependent variables. So that definition states that a sequence of random variables is said to be M-dependent if there exists a bounded M. Okay, so it will have M equals k minus 1, for example. So that if you put this block anywhere in your sequence, of k-mers or variables here, then the xi's on the left, the set of xi's on the left, and the set of xj's on the right are independent of each other. So all the dependencies are more local, and that's exactly what's happening with n-mut. That's exactly what our that lemma we just saw gave us. So n-mut is then the sum of m-dependent variables with this value of m. Now, the nice thing about m-dependent variables is that their sum is also asymptotically normal, and moreover, if we use Stein's method, we can also get the rate of convergence to this normal. Therefore, we can now apply the same type of strategy that is used to get hypothesis tests and confidence intervals for the binomial. And so we state this in what I call the main technique theorem, which is the main technique we're going to use here, which is that if x is the sum of m-dependent Bernoulli random variables, then with limiting probability alpha, x lies in this interval centered around its expectation plus minus the z-score times the square root of variance of x. Let me explain some of those terms. So the z-score, if you haven't seen it, it's basically the interval on a normal distribution that would capture alpha % of the data. And this is something that's very easy to look up in a table, or there's in a programming language you can usually have a function to compute this. So this width of the interval z alpha you have, and then the rest is the variance and the expectation, which you hopefully have computed. The limiting here refers to as L goes infinity, and this is often the case with these confidence intervals. The star here is to indicate that I'm hiding some detail that L has to be independent, and depending on how you apply it, for example, might have to be independent of K or of R1 in order for this to formally hold. But I'm not going to focus on that in the talk. So let's apply this then technique straight to n-mut, and we've already computed the variance, which I'm not going to plug in here, but we know it, and we have the expectation, and so we immediately get a hypothesis test for n-mut. Now, to compute a confidence interval, observe that this interval here is a function of R1, right? We have this RK, and this variance is a function of R1. And n-mut is something you observe. So for a given R1, either n-mut falls in this test range or it doesn't. And so what we are going to do, well, we could solve this equation for R1, and then we would get a confidence interval, but that's algebraically difficult, and we didn't pursue that. So instead, we just are able to numerically find the range of R1 for which n-mut, the observed n-mut, is in this test range. Okay, and in our paper, we have a proof of why this works. Now, let's go beyond n-mut. If we, for example, observe some variable that's a monotone function of n-mut, for example, Jacquard would be a monotone function of n-mut, then there's a corollary. if a variable belongs to an interval, that's true if and only if the monotone mapping of that variable belongs to the monotone mapping of that interval. Okay, so we have this general statement, and we can apply it to the Jacquard to have a confidence to have a hypothesis test for the Jacquard. Now the min-hash Jacquard estimator is a little bit harder because now we have two layers of randomness. We have the mutation process for which we can apply our main technique, but we also have this sketching process which has randomness from a hash function. And here our main technique does not apply because the sketch uses global information. So we use a different approach, which unfortunately there's no time to discuss, and we get also a hypothesis test for J hat, which again, unfortunately, we don't have time to even define this exactly in the talk, but it's all in the paper. Let's look at another random variable in this model, an island and an ocean, or sorry, the number of islands and the number of oceans. So what this is if you look at this sequence of k-mers, then you can partition them into islands and into oceans, which an island is a maximal interval of mutated k-mers, and an ocean is a maximal interval of non-mutated k-mers. So how do we get a hypothesis test for the number of islands? Well, we first write down this variable as a sum of m-dependent variables. In this case, for every position I, we can define whether it's a border or not. And it's a border if the k-mer at that position is mutated and the one in the next position is not. Then the number of islands is just the sum of the number of borders, and now we can apply the same technique that we discussed. So we derive this joint probability of two borders being 1. We confirm that the status of being a border is independent if the I and j is far apart. We derive the expectation and the variance of n island, and then we apply our main technique theorem to get a hypothesis test. This is the summary of our theoretical results, and I already discussed almost all of these. The one part which I didn't discuss is the coverage by exact regions, which is a random variable defined by McClott et al. In 2016, which we also studied and derived an interval for. Some experimental results. So looking at n-mute confidence intervals, what we did is we did a simulation where we started with a sequence with no duplicated k-mers, and then varied k and r, and for every value of r and k, we did 10,000 replicates, and in each replicate, we took the observed n-mute, we computed a confidence interval for r1 from it, and we checked, does the true r1 fall into that predicted interval? And we reported then the fraction of replicates where this is true. This is the definition way of checking, verifying the definition of confidence interval. And we see really good results for large L. As L gets smaller to 1,000, we still see very good results. As L gets to 100 now, we see this is where the L goes to infinity, starts to not hold for some values. We also did a similar experiment using not a sequence without duplicates, but the coli sequence, and we also see good results. We also tested the min-hash Jacquard estimator, and now I'm running out of time. So we basically replicated a table from the original paper, but instead of reporting the point estimate, we're reporting the validation of the confidence interval as a function of different sketch sizes and mutation rates. And we see, again, very good results, except for some extreme values of R1 and very small sketch sizes. Also, we did this with E. coli and got similar results. Finally, we looked at the application with read alignment. So one was Minimap2, which filters out alignments if the R1 estimate is far from the sequencing error rate, and it has its own way of estimating R1. But instead, we used our model to do our R1 estimate, and here, even as a function of different R1s, our we have a smaller error, the blue, than Minimap does in the red. In Java, which is a tool from McLeod et al., they have also a strategy for filtering out alignments, but instead of estimating R1, they measure the coverage by exact region. And this CBER, if it significantly deviates from the expectation, they discard the alignment. But they don't really describe what this significantly means. And in our case, we have a way to do this formally, to come up with a hypothesis test for CBER. Here you see the two lines above or below giving the 95% interval. And so we can discard reads which has a CBER score that's too low or too high. So to conclude, we took the simple mutation model, which has been, we didn't introduce it, it's been widely studied, but it's never been studied in depth as far as we know. And we looked at it in more depth, and we gave a technique for deriving hypothesis tests and confidence interval in this model. And this technique, what it does is exploits the fact that the K-mer dependencies are local. We then applied this technique to some natural random variables. And as I think is the big remaining question, I think theoretically is, you saw that in some cases the approximations don't work well. This is because they're only true theoretically for large L. And so, for example, this is normal. For a binomial, we know that when np times 1 minus p is low, we don't expect the normal approximation to be very valid. So it'd be interesting to derive this similar type of formula for m-dependent random variables. And this is the references, and I'll stop here. Thank you.
Thank you very much. So we already have some questions. What happens if the assumption of uniqueness of K-mers is relaxed? Does the analysis extend to weighted Jacquard?
I would have to think about how it would work for weighted Jacquard, but I do think that all the technique seems to rely heavily on this assumption of uniqueness. So yeah, I'm not sure how it would extend off the top of my head to the weighted Jacquard case.
Okay, thanks. Second questions. Could we think of updating this model to take into account random Bloom filter false positives and false negatives if we think of Lucas query filtration approach?
I think yes, Pierre. I think that just adds another. In a way, it should be like another chance that the K-mer becomes mutated, basically if it becomes a false positive. So I suspect that this could be taken into account, but one would have to think more about it.
Okay, thank you very much. So I think that thanks again, and we can move to Travis Gagey.
Right.
Travis on stage.
Everybody can see me.
Yes, we can see you, and you can start sharing your screen. And Travis is going to give a talk, R-indexing Wheeler graphs.
Okay, I will just start a timer. Actually, I can just watch the clock. Right, so people can see my slides?
No. Okay, now you start presenting. And let's see if they are also on YouTube. Yes, that's fine. Please go ahead.
Okay, so R-indexing Wheeler graphs. So this talk is I'm not planning to send this somewhere else, but it was something that came up in a paper that we were working on. It's a generalization of something we needed for that. Carlos will present that later. So what are Wheeler graphs? Those were presented. Giovanni gave an invited talk at CPM a few years ago when we came up. So a Wheeler graph is a directed edge-labeled graph whose vertices can be ordered such that those with in-degree 0 precede those with positive in-degree, and for any pair of edges E, U, V, and E prime, U prime, V prime, labeled A and A prime respectively. If the edge label A is lexicographically smaller than the edge label A prime, then the destination of the first edge has to be earlier in the order than the destination of the second edge. This is going to turn out like we came up with Wheeler graphs because we said we're generalizing Boris-Wheeler transforms to different kinds of data, and we're always proving the same kind of thing. What's the underlying what's sort of the underlying concept? And so there's this idea of if you have an edge, edges with smaller labels go earlier in the order than edges with larger labels, and then if two edges have the same label, then the order of the edges' destinations is the same as the order of their origins. Okay, so here's an example of a Wheeler graph. And here's the Wheeler order that shows that this is a total order on the vertices, such that, so it's not the only one. I think you could switch 7 and 8, for example, but this order works. How can you see that this is a Wheeler graph? Oh, well, okay. Why do we care about Wheeler graphs? So if G is a Wheeler graph, and we store a ranked data structure over its edge labels sorted by their origins, and partial sum data structure over the vertices in and out degrees, then later, given a pattern P in length of P log size of G time, we can find the interval in the Wheeler order containing vertices reachable by paths labeled in P. So this means if you consider the language of this graph to be the strings that label walks on that graph, then we can construct a compact and fast index for that language. So how do you do this? So you take this. Can people see my cursor? Anybody? Maybe. No. That's going to be difficult.
Yes, we do.
Okay, so you do see the cursor. Okay, because it's not important here, but it will be important later.
No, that's perfectly fine.
Okay, so so if you take this, you take this order on the vertices such that the first vertex within degree 0 has it's first in the order. It's 0, and then everything else, the things with incoming edges labeled A are earlier in the order. So this is a generalization of sort of suffix arrays. So this has the lexicographically smallest path. If you look here, it's an A, and then it's a C, and nothing else has a path labeled something smaller than AC coming into it. So this is 1, AG, this is 2. So if you put these the vertices and you write the labels on their out edges, this corresponds to a Boris-Wheeler transform. And then of course the labels on the in edges are just sorted, so there's no in edge, and then a bunch of A's, a C, a G, and a bunch of T's. How does this index work? Well, from the Boris-Wheeler transform, you can actually get this graph back. From the Boris-Wheeler transform in the in and out degrees, you can get the graph back, because if you look, the A's all have to go to vertices that are together in the A part of the interval. And the C has to, well, there's only one C, so it goes after the A, and then the G has to go after the C, and then the T's all have to go together. So the key idea is, if you look at these arrows, when you look at them all together, it's a mess, but if you look at them separated by characters, these lines don't cross. So if you know this is the third out edge labeled T, it has to be the third in edge labeled T. And because it's easy to store what the in edges are because they're sorted, okay, then so you can rebuild this. So it's the same kind of thing that we've been doing for ages and ages with Boris-Wheeler transforms based data structures. So the mnemonic for this is, remember that these edges don't cross. The streams, no crossing the streams. So in the next talk, Nicola Cotemacho will tell you about how you can cross the streams a little bit, but for this talk, no crossing the streams. So just as a quick example, keeping track of the time here, as a quick example, how would we find the vertices that can be reached by paths labeled TA? Well, the first thing is all of the vertices can be reached by paths labeled empty. And so from here, we can say, okay, from this interval of all the active nodes, we consider all the things that can be reached with T. So they're the interval here from 6 to 9. And so these are the vertices that can be reached by edges labeled T. And then from there, where are the edges that labeled A leaving this interval? Well, they go here. So the only vertex that can be reached by TA is 3. And it can actually be reached two ways, TA and TA. Okay. R indexing. So this is from a paper a couple of years ago. Let S be a string and let R be the number of runs in a BWT of S. We can store S in O of R space such that where R is the number of runs in BWT, in O of R space such that later, given a pattern P in P log length of S time, we can find the interval in the BWT containing characters preceding occurrences of P and S, and then report the locations of those occurrences in log S time per occurrence, length of S. So the key thing is being able to report the locations of the occurrences fast. So I won't go into too much detail about how this works. Also, Nishimoto and Tabe sped this up so that now they can get optimal length of P plus awk time when the alphabet size is polylogarithmic in the length of S. Just really quickly saying how this works. What you're going to do is at the run boundaries in the BWT, you store pointer. You store sort of the suffix array, the position of the in this case, the successor. Okay, so if you look at 33 and 34, why is there an arrow here? Because the 33rd character is a C and the 34th character is a G. They don't match. They're a run boundary, so we store a pointer from 33 to 34. 37, the 37th character is a G, the 38th character is a T, so we have a pointer. Why don't we have a pointer here? Because the 50th character is a C, the 51st character is also a C. So these aren't all the pointers you would store, they're just all the ones I need for this demonstration, and actually they're a fair fraction of the pointers that you would store at the run boundaries. So using the magic of something called the toehold lemma that we didn't do, so if you want to know about it, it's Polykriti and Pretza, you can find the lexicographically first occurrence, the first prefix, first prefix that ends in TA. So you find this one. So now it would be cheating for me to show you how to find the other ones using with all of this information written here. So let's make that go away and let's see how this works. So we found this red circle. How do we find the other occurrences of TA? Well, I'm going to follow this line until I hit one of these dashed pointers. Okay, and I'm going to keep track of how many steps that are. Now, I'm not actually going to do that step by step. You do this with a successor data structure. So it's 2, I follow the pointer, and then I go back 2. So this is also an occurrence. Now here, I follow to here, which is 11 steps. I follow the pointer, and then I go back 11. So this is also an occurrence. Here, I follow here, which is 5. And then I follow this pointer, and then I go 1, 2, 3, 4, 5. That's an occurrence. Here, I follow to here, which I don't know how many steps that is. I drop down, I go back. That's an occurrence. Here, I go to here, which is 2 steps. I follow the pointer, and then I go back to 2 steps. That's an occurrence. Here, I go to here, which is 1, 2, 3, 4, 5. I drop down, and then 1, 2, 3, 4, 5. that's an occurrence. Here, 0 steps. I go to here, that's an occurrence. I follow the pointer, 0 steps. That's an occurrence. I follow the pointer, 0 steps. That's an occurrence. That's 0 steps. That's an occurrence. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's an occurrence. And now I found them all. Okay? How does that work? It's magic, and I don't have time to explain it. Okay, so why would you want to put these things together? What is the result? So this is, let G be a Wheeler graph, and let R be the number of runs in the Burroughs-Wheeler transform of G. Suppose G can be decomposed into upsilon edge disjoint directed paths whose internal vertices each have in and out degree exactly 1. These are unitigs, okay? So upsilon for unitig. We can store G in O of R plus upsilon space such that later, given a pattern P, in length of P log G time, we can count the vertices of G reachable by directed paths labeled P, and then we can report them in log size of G time per vertex. So this isn't actually that hard. We're just we're taking the unitigs and we're treating them, the upsilon unitigs, and we're treating them as like strings. So it might be interesting. I don't know if you can use Nishimoto and Tabe's technique to get a speed up here too. When the alphabet is polylogarithmic in G. Okay, so how do you remember this? It's upsilon is the number of unitigs, and I tend to say oops a lot. So we needed this for a special case of this for a paper in a theorem in a recent paper Garance will present later about long and stringy trees. It's actually easy to prove the general theorem, more so than to explain why we want it. Wheeler graphs are cool, R indexes are cool, so R indexing Wheeler graphs is really cool. Yoni Siren actually says he's implemented something like this, so it may be useful for something. And Nicola Praca has a more sophisticated result in the SOTA 21 paper about trees. Not sure that's practical. So I want to talk about tunneling, which isn't my idea. It's from Uwe Bayer. Uwe introduced tunneling to reduce the number of times we need to write large run lengths in a run length compressed Burroughs-Wheeler transform. We can put paths in a Wheeler graph together in a tunnel. So you're going to take a Wheeler graph and now you're going to squish it. So you can take two paths and you can squish them together if the corresponding edge labels match and the corresponding vertices ranks are incrementing in that Wheeler order. And you do this, but you stop one edge earlier than you would think. So let's see an example. How did I get this graph? Well, I merged these two paths. And you can't merge this bit because it's different, but you can merge these vertices and these vertices and these vertices, and then you stop one edge earlier than you think, and then you can merge these vertices and these vertices, these vertices and these vertices. Okay? So here's a more complicated example. So you notice that this stuff is similar, 0, 1, 2, 3, 4, 17, 18, 19, 20, 21. Now, and then over here, this doesn't look, it's 49, 45, that doesn't look, but it's 45, 46, 47, 48, 49, so you can merge them. 8, 9, 10, 11, 12, you can merge them. Okay, so what do? You identify these blocks, and you stop one edge before you think you would. So these are all C's, these are all A's, these are consecutive, but you don't do that because that would be the last step. So you merge them like this. Now why do you leave this last step and you don't go as far as you can? Because these edge labels are all the same, so the order of these vertices, these edge labels are the same, the tunnel labels are the same, so the order here is the same as the order here, 5, 1, 2, 3, 4. Whereas if you look at the order here, it's a different order, because these edges don't match. So the idea is, this edge, this is 5th when you go into the tunnel, so it's 5th when you come out of the tunnel. So the lexicographically largest thing going in is the lexicographically largest thing coming out. Okay, so it preserves the ranks. So you're not actually losing information or changing the language of the graph when you do this compression. So you can index a tunneled Wheeler graph so as to prevent false positive chimeric matches, which are bad, maybe. So in our example, if the first variation is CAT, the second variation isn't TC, and maybe you don't want to include things with CAT and TC in your index because maybe if you have CAT, then if you have TC, it will kill you. So if you didn't observe a pair of variations together anywhere in your index population, you don't want your index to match that. And you can, like if you do filters and colors and stuff like that, you can get rid of it later, but this means you can't get nice bounds, so maybe you just don't want your index to return that anyway. Okay, how do you remember how this works? I found out while doing these slides that this is called a loom tube. So just think of the tunnels as the tubing for your wires, your loom tubes, and tunnels are FIFO, first in, first out. Now in this case, it's lexicographically first in, it's lexicographically first out. Okay, so why do you want this? So here's why would you want to R-index a tunneled Wheeler graph? Because the tunneling takes advantage of the repetitive structure, so it already collapses the runs. So wouldn't a standard sampling be better? So if you're already trying to take advantage of the runs of the repetitiveness when you're tunneling, can you then try to take advantage of it again for R indexing? So I was thinking, suppose the conserved regions between variation sites are on the order of 1,000 base pairs, and the probability of a base pair mutating is on the order of 1 in 100 million. So I'm not sure about that. So you can read the footnote. I think it might actually be smaller than the probability might be higher than that. And suppose we're indexing 1 million genomes. So this is pure speculation. We'd like to tunnel the conserved regions, but how do we deal with the mutations? Well, people tend to sort of want to filter out the mutations, but I've seen this in a movie where people try to get rid of the mutations, and it doesn't end well for them, so we shouldn't do that. The conserved regions of about 1,000 base pairs are going to be broken up in expectation by about 10 mutations each. So if we merge the paths in the conserved regions into about 10 tunnels, then we should still get a significantly smaller, interesting Wheeler graph, but the Burroughs-Wheeler transform is still going to be run-length compressible. So I was supposed to finish at 11:40 my time. Happy year of the ox. Happy belated birthday to Moni, who you heard about a little bit in Dominic's talk this morning. And are there any questions?
Yes, thanks again for the talk. And yes, I'm inviting questions in the chat.
So I'll stop sharing so I can actually, well, maybe
yeah, sure.
That way I can actually see things. Help? No, I can't.
Yes, no questions so far.
It felt like that went faster than it probably did. But
no
questions, 2, but they're probably answered. Yes. So yeah, you can tunnel a Wheeler graph, and maybe it's actually something you might want to do. You can R-index a tunneled Wheeler graph. The main thing. Okay. So it's time for Nicola's talk. So now he's going to tell you about how crossing streams is okay.
No, that's okay. I mean, there are no questions, so I want to thank Travis again for your talk. And next speaker is Nicola Cotumaccio. who's going to give talk indexing and compression from Wheeler graphs to arbitrary graphs. So please share the screen over the window.
Yes, can you hear me?
Yes, everything is fine. Please go ahead. If you want, you can maximize. Okay, that's perfect.
Perfect. Okay, so I will try to show the similarities between what I'm going to say and the previous presentation. And indeed, both presentations start from Wheeler graph. I guess that Travis already gave a good idea why Wheeler graph were introduced and how they are connected with the Barrows-Wheeler transform. So what I'm going to show now is how it is possible to actually generalize the mechanism of Wheeler graph. Okay, I will just recall a little bit the definition of Wheeler graph. We have just seen it, but so I hope that at least at the end of the day, the definition of Wheeler graph should be okay after these two presentations. So intuitively, consider a graph or an automaton. Basically, it's the same structure. This is just a technical difference we make in the paper this presentation is based on. And so we say that this automaton is Wheeler if we can define a total order on the set of nodes having the following properties. The start node of the automaton must come first. Second, as you can see in this example, all nodes labeled A come before all nodes. So this node is only reached by some edges labeled A. This node is only reached by some edges labeled A. This node is only reached by some edges labeled A. Here B, B, C, and C. So I should respect the order of the letters, the alphabetical order. And the last property that I require is that if I consider any two pairs of two edges with the same label, then the mutual order of the start states should propagate the mutual order of end states. So for example, if I pick this edge and this edge here, then I have that 2 is smaller than 6, and consistently I have that 7 is smaller than 8. There's also this other example here with letter A. I use this example just to show that the definition is also consistent with a situation where I actually reach the same state. So in general, I just require that if this is smaller than this, that this state should be smaller than or maybe equal to this one. So this situation is consistent with the definition of Wheeler graph. And the reason why Wheeler graph are useful, I think was already given by Travis. And the reason is that I managed to, if I want to read patterns on the graph on the automaton, then what I obtain every single time, for example, if I start from the start edge, from the start state, and I try to read some considered string, for example, A, B, C, C, B, A, then I should end up in a set of consecutive states. And the reason why this actually works is that if I consider all strings recognized by state I, that is all strings that I can read, for example, starting from the initial state and ending in state I. So, for example, in the case of state 3, these strings are A and AA. Or, for example, in the case of string of state 5, these strings are B, A, B, A, A, B, and so on. Then these sets, respect the total order on the states of node from a lexicographically point of view. So this should be a bit more clear if I show this slide. The point here is that here I'm just repeating what I'm just explicitly writing what I just said. So for example, I3 is AA, A, and so on. And you can see that if I consider the colexicographic order, that is the order that compare two strings starting from the last character and proceeding backward, then this string is smaller than this string. This string is smaller than this string. This string is smaller than this string. This string is smaller than this string, and so on. So except for intersection, then every string here is smaller than every string here. Every string here is smaller than every string here, and so on. This works for, this is a consequence of the definition of Wheeler graph. But now let's try to change perspective compared to the previous presentation. So in the previous presentation, we started from the Barrows-Wheeler's algorithm, and we said that Wheeler graphs are a good way to capture how the Barrows-Wheeler transform works. So now let's change perspective and let's start from Wheeler graph. So now it is possible to interpret every single graph as a Wheeler graph, as a Wheeler automaton. Unfortunately, if I just keep to the standard definition of Wheeler automata that I've just given, this is impossible, because if I consider the language interpretation of Wheeler graph, that is the expressive power, then I can see that if an automaton is Wheeler, then by using only Wheeler automaton, I'm able to capture only a very small subclass of regular languages. So, for example, if I consider unary languages, I mean languages whose alphabet consists of just one letter, then it is easy to see that such a language is Wheeler if and only if it is either finite or co-finite. So, the idea of the paper that I'm presenting is to try to maintain the structure, the idea of Wheeler graph, but somehow changing in such a way that it can be applied to generic graphs. So, okay, I like the fact that I can rely on intervals, that I have this easy way to follow strings, as for example, Wheeler explained in the previous presentation. I can very easily keep track of patterns that I read on the automata. But since this is impossible for generic graph, is there a way to adapt this mechanism in such a way that it can be applied even in more general situations? And the answer is positive, is yes. And the intuition is the following. In a Wheeler graph, what I require is a total order on the set of states. And this is just the formal way of writing the example that I presented earlier. That is, if I consider a state reached by edges labeled A, they should come before states reached by edges labeled B, which should come before states reached by edges labeled C, and so on. And here, axiom 2 is simply the comparison property between two edges with the same label. So the intuition is that we can drop the assumption that the order is total, and we can be fine with just the requirement that the order is partial. We don't need to change axiom 1, and we slightly need to change axiom 2. If you recall the example, in axiom 2, I was requiring that the mutual order of starting states should propagate to the mutual order of end states. Here, I'm just requiring the opposite. That is, the mutual order of end states should propagate to the mutual order of start states. In the setting of Wheeler graph, this is 100% equivalent to the old definition, because I'm just picking the contrapositive statement. But remember that now we are just considering partial order. So these two statements are not logically equivalent any longer. So this is the definition that we introduced in our paper. And the reason why we needed to change axiom 2 is that as I try to show, the enjoyable properties of Wheeler graph strongly rely on colexicographic order on strings. And colexicographic order on strings works backward. So I start from the end of the string, and if the last two characters are equal, then I proceed backward. If they're equal, then I still proceed backward, and so on. So the idea is that in order for this to work, I need some backward compatibility, not a forward compatibility. I guess the reason why, I may ask Travis, I don't know, the reason why in the original paper Axiom 2 was defined the other way, that is in such a way that a forward compatibility was guaranteed, is that this forward process is the process that is needed to find a pattern on the graph. But from a logical and from a structural point of view, here what we need is a backward compatibility in order for things to work fine. And the reason why this definition is more general than the previous one is that now it can be shown that every single automaton admits some ordering with these properties. And the intuition is that as one may expect, the reason why this always works is that now the order does not be total, it can also be partial. So letting the order be partial is basically what was saying Travis before. If the order is partial, I'm allowing some edges to cross. Okay, I say I don't care about some edges crossing. But from an algorithmic, from a computational point of view, we will see that the more the order is close to be total, the better. So just a very quick example. Consider the automaton in the figure. It can be easily shown that using some well-known properties of Wheeler graph that this graph cannot be given a Wheeler ordering. Basically, the reason is that here there is this cycle. But we can, for example, define a partial order which satisfies the properties that I've just presented. Such a partial order, for example, may be the one given by the Hasse diagram on the right. This can be easily checked. Now the point is, if I, in general, consider a partial order, then I can divide all the elements of the partial order into a number of totally ordered subsets. This works for every single partial order. In the worst case, I just pick singletons, but for example, in the case of this partial order, I can pick 0, 1, 3, 6, and 4 to 5, because this means from this diagram it follows that every two pair of elements here are comparable and every two pair of elements here are comparable. This is just very general. And there is a well-known theorem, Dilworth theorem, stating that the cardinality of a minimum size partition into totally ordered sets is equal to the cardinality of a largest anti-chain in the partial order. An anti-chain is simply a subset of elements such that every two elements in the subset are not comparable. So, for example, here the subset consisting of 3 and 4 is an anti-chain because 3 and 4 are not comparable. And since we have explicitly shown a partition into two elements, by Dilworth theorem, it follows that, for example, it can exist an anti-chain of cardinality 3. That is, if I pick any three elements here, then at least two of them must be comparable. So it makes sense to measure the complexity of a graph of an automaton by considering the smallest p, the smallest cardinality of a partition into totally ordered sets. The point here is that in general, a graph may admit several such orders. So in order to obtain a measure that only depends on the structural complexity of the graph, I should consider all possible lexicographic order on the graph and then picking the smallest such cardinality of a chain partition. So now it makes sense to say that this P somehow says how much a graph is difficult, is complex. And from the previous discussion, it follows that a graph is Wheeler if and only if this quantity P is equal to 1. because a graph is Wheeler if and only if the order is total, and trivially a total order admits a partition into just one totally ordered set. So in general, all results. As I was saying earlier, all algorithmic results depends on this quantity p, and as one may expect, the lower p, the better. This is an explicit definition of a colexicographic order which works for every single graph automaton. So now every automaton is this quantity p that can be associated to the automaton. I will skip details. And as Travis was saying, the nice property of Wheeler automaton is that if we start from, if I want to read a string starting from the start state, then I always end up in a set of consecutive state. More generally, the property is the following. If I start, for example, from some consecutive states, 2, 3, 4, 5, and I read a letter, say C, when I say I read a letter, I just mean, okay, just pick every single state I start from, 2, 3, 4, 5, and consider all edges that I can follow by reading C. So from 2, I can go to 7. From T, I can go nowhere by reading C. From 4, I can go nowhere. And from 5, I can go to 7. So to sum up, I end up in this set of states. And once again, I get an interval. So this means that by induction, in general, if I start from an interval and I read a letter, then I end up in an interval. Then if I read once again another letter, I still end up in an interval, and so on. So if I read a string in general, then if I start from an interval, I end up in an interval. And now the only difference for generic graph is that in the worst case, I need not keep track of just one interval, but I need p intervals. And now I don't have time to show details, but what can be shown is that actually all compression and indexing properties of Wheeler graphs still work. In other words, it is easy to generalize a compression representation of Wheeler graph to colexicographic automaton. So this kind of graph can be compactly stored. This means that the complexity of the storing mechanism basically depends on this quantity p. And in order to in order to read a string, as I just said, I need to keep track of p intervals. And this can be done by the same mechanism or the forward algorithm that is used, for example, in FM index. This is just a generalization where I don't need just one array. In the standard forward algorithm, I need a number array. Now you just have to think that you need the whole number of arrays multiplied by p, because I kind of need an array for every interval, but the general idea is the same. Okay, I'm not going to present this. This is just a way of comparing Wheeler automata and arbitrary automata. And I just mentioned that there are also some consequences, some more theoretical consequences about Wheeler automaton, because they somehow describe how much an automaton is non-deterministic. But okay, this is just a very interesting theoretical result, but probably it's not directly connected with what I just explained. Okay, I guess this is what I meant to present, at least to give a glimpse of the computational and algorithmical application of colexicographic automata. Yeah.
Thank you very much, but you have 1 more minute, so if you want to show the slide of the further directions, that might be interesting.
Okay.
We're not late, so that's not a problem.
Right, I don't know why. Okay. Yes, in general, when I turn a non-deterministic finite automaton into a deterministic finite automaton by the standard power set construction, what happens is that I obtain a blow up in the number of states. That is, if I start from an n states, then the number of states that I obtain is exponential in the number of states of the non-deterministic finite automaton I started from. So what we actually showed is that it's true that in worst case we obtain an exponential number of states, but this number is not exponential in the number of states, but it's exponential in this quantity p. So this means that it was already known that Wheeler automata are very special because they are a class of automata such that if I transform a non-deterministic finite automaton into an equivalent deterministic finite automaton, then I don't have this exponential blow up. I just have a linear number of states. But even in general case, this blow up must be exponential, but the quantity that makes it exponential is p, is not n. So this means that all problems that are difficult on non-deterministic finite automaton can be turned into easy problems on deterministic finite automaton by applying algorithm, by simply transforming the non-deterministic finite automaton into a deterministic one, and then I obtain algorithms that are fixed parameter tractable with respect to this quantity p. So this just shows once again that this quantity p seems to nicely describe the complexity of the graph.
Okay, thanks again. Are there any questions? Let's wait a little bit if somebody has some question. So it looks like there are no questions. So thanks again for your nice talk. And I'm inviting to the stage the next speaker, who is Garance Gourdel. Hi, Garance. Garance is going to give the talk. One moment. So if Nicola can get back, because we have the first question. Okay, Nicola, so have you tried computing P for some regular expression?
Yes, indeed, it was one of the things that we planned to do. For example, it's possible to show quite easily that the quantity P can be nicely, I mean, there is a very easy dependence between a language I start from and some Boolean operation that I make on the consider or the consider languages. So, for example, if I start from a language whose P is equal to P1, I start from I pick another language whose P is equal to P2, and for example, I take the union, then in the worst case, the resulting P is equal to P1 plus P2. So this somehow suggests that I can describe the complexity, the hierarchy of regular languages seen as regular expression by in P. Yes, let's say that we are trying to work on this, but it's still on progress. Still, it seems to work quite nicely, yes.
Okay, thanks again. Thanks again, Nicola. And so Garance Gourdel is going to give the talk XBWTing read sets. So I think that you have already shared your screen.
Okay.
So I think that you can maximize the slides.
The window. Now you see it well?
We see your screen. What you see, we see your entire desktop.
Okay, but now the slides were in full mode.
No,
So
maybe you can stop sharing and share only the window of your application.
Course. Good.
Okay, that's perfect. Perfect.
Is
Please
it
go
good now?
ahead.
Perfect. Very much. I'm very happy to present today to DSB. I'm Garance Bourdel, a PhD student supervised by Pierre-Peter Longo and Tatiana Stariskovskaya, and this is a joint paper with Travis Gaggi and Giovanni Manzini. And probably my presentation will be a bit shorter than planned, so and I imagine there won't be a lot of questions, so I'll take my time anyway. This is a presentation on XBWT in read sets, and I've gave it a subtitle that is taking advantage of the read alignment to obtain better compression. The starting point is the FM index, which is a data structure based on DBWT that both compresses and indexes. It's a in short aligner, short read aligner such as Bowtie and BWA. And it has been recently improved to support O of R space R to be the number of runs in the BWT, as I think Travis mentioned, and goes to operation count P in the complexity of the size of the pattern P, and locate in P plus the number of occurrence. And so all the compression in space is based on the number of runs in the BWT. And if we take an example that is going to be our running example in this presentation, it's gata. If we take the it has 8 runs. And the question we have is, could we have the same type of structure that would have similar performance based on the number of runs in the BWT or the EBWT or the XBWT? And also, how can we have the minimum, smallest possible number of runs without going into optimization, just thinking about this as the goal? Then a first idea to build an FM index for the read set is kind of the naive approach, where we could concatenate the reads with just dollar as a separator, and then build the FM index for the entire string. So in our example, this gives us this string where all those reads are gata, taga, taga, gatak, and atagat that are going to be the reads we always take in our examples. And if we build the BWT, we have 20 runs. And the issue with this approach is that computing the BWT for such a long string is challenging, and also the context before dollar doesn't really make sense. So if we have two suffixes of 2 reads with the same prefixes, then maybe it doesn't make as much sense to compare before the dollar. So the number of runs, the dollars in the BWT actually break some runs, just as here that you can see. And so it might not be optimal. Then there is the EBWT, which stands for the extended Burroughs will, where you permute all the in the string into the lexicographic order of the suffixes that immediately follow them, considering each string to be cyclic. And we take always the same example, the same reads, and we get this results, this extended Burroughs-Wheeler transform with 19 run. And the good thing is with this approach is because we consider each string to be cyclic, we don't have the entire string, so it's easier to build and to update than the naive approach. But the problem we have is that all those reads are taken from this original string gatacat, and still the number of runs in the EBWT is more than twice the number of runs we originally had on the strings, that was 8. So we can also talk about the heuristics to the reads to get a better compression of the EBWT. There is first the reorganizing of the reads in reverse lexicographic order, or colexicographic order. And if we do that, we actually found the same thing as before, because they were already in reverse lexicographic order. and so 19 run. Then there is Spring, which is a separate software that attempts to reorder the reads according to their position in the genome. That without having the position in the genome, as guessing some position in the genome. And in this case, it does worse than the original RLO EBWT we had. Then there is a separate data structure known the XBWT for extended BWT. That is a generalization of the Bose-Wheeler transform for label trees, where the characters get sorted on according to the level of their outgoing node. So we first have the node that is labeled epsilon, the root, that has AB as its children. Then we have this node that is just labeled A, so we have ABC, then and so on. It can also be seen as a subcase of the Wheeler graph, which I thought would be interesting to mention. And also in the paper we prove the results for the general case, the general Wheeler graph case, and then apply it to the XBWT. And our approach is quite simple. The idea is that, okay, but if we have the reads that correspond to a specific known assembled genome, could we use the genome as an additional context for better compression? So in the example, this just means, okay, we take always the same reads, we align them, and we create this tree structure where we have the original genome in the medium, and the reads branching out of the main trunk. And this, the XBWT of this tree gives us is this, and has only 7 runs, which is the same as the BWT of just cat without the dollar. And this is no surprise because we can actually prove that if we create such a tree where the reads are errorlessly sampled and aligned to the reference, meaning there are just no difference between the main branch and the reads, then the XBWT of the tree has the same number of runs as the BWT of the reverse of the reference. Then we also show in the paper, this is just a preprint that I'll link at the end of the presentation, that if it's such a level to is there an issue? No, okay. Everything seems to be going well.
Yes, sorry to interrupt you, but it looks like there are some internet connection problems, and so at a certain point the slides have been stuck, so we have not been able to look at the last few slides. I don't know, maybe, and at the very end your screen share disappeared.
Okay, so I'm already in the loop.
Try to resume your screen sharing, and yes, a suggestion is, can you lower the definition of your
I've
screen?
Already lowered the definition,
okay,
I'm sorry.
So another thing that you can try is maybe to turn off your webcam, turn off the image at least.
Yeah, I think so.
So let's see if it helps.
Okay.
And okay.
So at what slides did I lose you? Because
okay, no, I don't remember these slides. No, yes, go ahead. But we also have a problem because on YouTube there. Can you try to enlarge your PDF reader before sharing? Because otherwise, yes. Now, resume sharing, please.
Okay.
Stop sharing.
The thing is, I can't do it on. I can't do it on at the same time. I'll try, but I don't think I can.
Okay.
So I can share my entire screen, but I don't think I can else share
Let's try. I will tell you if there is anything that is not. Let's see, because it's on. Okay. Okay,
Is it okay?
That's better. That's better, because the problem is on the YouTube stream that.
Yeah, I can imagine that it's only very vertically.
Okay.
So, did you see the slide on the explanation of the XBWT?
I don't remember this slide. I think you have to go back. Yes, this one was no. Go ahead. This one. No, this one exactly. This at least to my recollection, this one was the last slide.
Okay. I'm gonna start a bit again. Just
okay. It seems that somebody confirmed my what I meant.
Okay.
So thanks. Go ahead, please.
So I'll resume here. I was explaining a bit the XBW. And it's better to resume there as it's literally in the title of the presentation. And so this is the extended Burrows-Wheeler transform, but with next, that is the generalization of the Burrows-Wheeler transform for level trees, where the characters get sorted according to the label of their outgoing node. If we look at this tree now that you can actually see it, there is the root that is level epsilon, and so we have the two characters following this node, then the root level A, so we have A, B, C, then AA, and so on. This data structure can also be seen as a subcase of the Wheeler graph, and then our approach in this technique is that if this reads corresponds to a non-assembled genome, we can actually use the genome as additional context for better compression. This means that in our example, okay, we can have the reads aligned perfectly, and this gives us this tree where the reads are just branching out of the main structure from where the reads are extracted. And then the XBWT of T is this, which only has 7 runs, which you can remember is better than all the XBWT had. Then this is not a surprise, because we can show that if we create such a tree, meaning main reference and reads that are errorlessly sampled and aligned to the reference, then the XBWT of the tree always has the same number of runs as the BWT of the reversed reference. Then we also show a result for the graph, but here we apply it to the label tree. And if we have such a label tree, and we let R be the number of runs in the XBWT and T be the number of reads, then in space R plus T, we can compute locate P in the size of P plus operands plus times a log n factor. So the problem with this is just that in reality, the reads we have to index are not perfectly matching the assembled genome. So how does this approach to compression work in practice? And I first wanted to digress a little bit on the most technical part of this talk, that is going to be mentioning that we actually choose to build the XBWT via a prefix repassing construction. So I think the next talk will be focused more on this, and someone has brought this concept before. And just I wanted to explain quickly the 3 steps we can have in the prefix repassing construction. First, there is a scan, where we just slide a window onto the string, compute the character fingerprint of the window, and the windows that have a character fingerprint modulo P of 0 are breaking windows that are going to determine different phrases in the text. And all those phrases will be prefix repassing because of this window construction. And so in our case, we scan the reference, creating a parse that is the ID of the phrase and the dictionary that stores the link between the ID and the phrase. And then for each read, we first have to extend the read so it starts with a window that had a hash of 0 and ends with that. So we keep the property that it's prefix free, and then pass the extended read to construct the same path. Then we actually build, in the next step, we actually build the XPWT of the parse. And then in the final step, we build the suffix array and the longest common prefix for all the suffixes of the words in the dictionary. And for each suffix, we add the correct character depending on the cases. But actually, for this presentation and the experiment result, this has no importance. As for now, we only have experiment results on the number of runs. So the XPWT is always the XPWT. The way we construct it is not relevant for now. And to compare only the number of runs and so the compression behind it, we compare to the eBWT. We always use the rope BWT2 implementation to refer to use to compute the eBWT. And we compared it, to be fair, with and without the $sign, as our approach doesn't have any $signs. Then we compared it to Spring plus BWT. I remind that Spring is a reordering of the reads that improves diminishes the number of run lengths. Still with and without the $, and the RLO plus the BWT with RLO is reverse lexicographic order. That is also supposed heuristic to improve the number of runs. So what we found is that the number of runs was always greater in the eBWT, then a little bit lower in Spring plus eBWT, but then much lower in ILO plus eBWT. So in the next graph of comparison, we always compare ourselves to ILO plus eBWT. Then we compared our the two implementation and the number of runs in the two implementation on several data sets. First, a synthetic one where we could generate the reads and have a controllable error rate. Then on real words, but only the reads that match it to the genome and not to the reverse complement of the genome. This is important because the reads tend to have more error towards the end. So when a classic aligner aligns to the genome, those reads that map to the reverse complement of the genome get reverse complemented, and the error then are at the beginning. So for now, we put them aside, as the solution in long term will be to index those to another tree that has the reverse complement as the main trunk, but for now we just leave them aside. Then E. coli has the real world dataset that we used is E. coli from the single cell datasets, Staphylococcus aureus from the single cell dataset, and Hydrophilia from the GHB datasets. I'll first start by showing you the result on the synthetic data. To be a bit clearer, we generated this synthetic data with a WJSim, and we tested for various error rates between 0 to 2%. And we generated always 20 million reads and of length 100 base pair. By default, there are 15% of the polymorphisms that are indels and with their lengths drawn at random from a geometric distribution. So we have this graph where we can see that for 0%, E. coli is just the sequence from which the reads were extracted by WJSim. Then we had a very good compression. Much better as it's in millions of runs. You can already notice that removing the reads is already quite a significant change, and it's important to note to compare. And then for various error rates, we still do better We didn't go above 2%, but for 2% we do better. Also, it's interesting to know that on the chromosome 19 that we also start, we do much better. And we are happy to see that only on synthetic data, but still is there a new issue? Yeah, okay. My screen sharing stopped, no? Okay. That's a bit annoying.
Yeah, I'm sorry.
No problem. It's not your fault, my internet connection is bad.
It's,
Yeah, but we lost only the few seconds, a few last seconds.
yeah,
Okay.
yeah.
Almost everything was fine.
Okay. Then I'll restart sharing. Okay, share.
Yes, just a few
Okay.
seconds, just to be sure that on YouTube we can read it fine. Yes, that's fine.
Thank you.
Go ahead. Thanks.
Sorry, I'm causing you so much trouble. So we are happy to see that even for 2% we are doing better, which is way above the commonly assumed error rate of the 4 tweets, that is generally 0.1%. Then there are experimentation on the real data, and as always, real data is a bit more complicated, and we are still doing better on the E. coli dataset. We are doing slightly better on the Staphylococcus dataset, but quite similar. And interestingly enough, we are doing quite bad on the hydrophilia aligned to the genome assembled by ABES. And we are doing better on the alignment to the reference, but that's also biased because not all reads get mapped. So the reads that get mapped, we do manage to compress a little bit more. We do not exactly have an explication for the hydrophilia result because there's a better aligner than this, but it still gave similar result. So if you have any idea, we would be very happy to know. Still, for the E. coli datasets, just removing the dollar signs decreases the number of runs by 16%, and then moving to the expandability reduces by 8.2%. So we think it is still a valuable option to consider. And then it's a very early work. There is quite a lot of to-dos on the experiments. First is an evaluation on maybe the human genome, as we expect there will be less diversity in the genome, so it should be beneficial for our compression that needs to be as close as possible to the main trunk of our tree. Then there is the actual FM index construction that hasn't been implemented and its time analysis, and also the time comparison of the prefix-free construction of the BWT compared to other construction of the BWT like BWT channeling or Wheeler sort. And I wanted to finally mention that we can see a possible application of this idea to the hybrid index because this picture from a paper on Journal 3 Stringy by René David Weiss and Knut Reinert is quite similar, and we think it might be interesting to consider sorting the XBWT of storing the XBWT of Journal string 3 rather than storing the BWT of a string kernel. So thank you a lot for your attention and your patience with the technical difficulty. The takeaway message is, for compression, really consider removing the dollars. It's important. And taking advantage of the genome for additional context can bring a much better compression. And it's a trail to consider. You can access the pre-publication here or via the QR code. And if you have any question, I would be very happy to answer that.
Thanks for your talk. And I'm especially impressed by how you coped so graciously with the internet connection issues. So I'm asking if there are any questions. I'm going to wait a little bit because also for last talk, questions have been a bit slow to arrive. And
Travis can always manage to find a question, but he's on the paper, so it makes sense. Okay, I'll stop sharing screen.
Yes, so let's... okay, so I can see no question even on YouTube. So thanks again for your slide and sorry. Okay, no, one question. Did you try this approach for long reads?
Not yet. I think it will really. I don't know long reads as well, and the question is depending on the error rates and how where the error occur. This is going to be the concerning point to apply to long read, I think. Thank you a lot for your question.
Okay, thank you very much, and thanks again for your talk. So I can now introduce Massimiliano Rossi, who is going to give a talk, PFP compressed suffix trees. So Massimiliano, may you please try sharing your screen? Okay, let's see on YouTube. That's perfect. So
okay, can you hear me well?
Yes, that's perfect.
Okay, great. So, hi, I'm gonna talk about PFP compressed suffix tree, and this is a joint work with Cristina Boucher, Andre Quaccio, Travis Gheghi, Jan Holub, Giovanni Manzini, and Gonzalo Navarro, and this was presented at ALENX this year. So, let's start. Okay, suffix trees. So the suffix tree is one of the most powerful data structure in stringology and bioinformatics, and it was introduced by Weiner in 1973, and is the compact tree of the suffixes of the string. It is extremely powerful. It is able to index all the quadratic number of substring of a string in linear time and space. And it's heavily applied in stringology and bioinformatics. And for example, you can find maximal unique matches, maximal exact matches, tandem repeats, and many other things. And those all those has application in bioinformatics like sequence alignment, short read alignment, and so on. Okay, now we are talking about bioinformatics. So why don't we want to index one human chromosome? For example, the chromosome 19 with just one C and not two Cs. So the chromosome 19 is 48.5 megabytes pairs long, and it can be compressed using gzip into 16 megabytes. With a classical implementation of a suffix tree, we will need 1.2 gigabytes to index just one chromosome 19. We want to scale up. So let's say that we take 512 human chromosome 19 haplotypes from the 1000 Genome Project, which are like around 30 gigabytes pairs, which is more than one full human genome, which is 3 gigabytes pairs, more or less. They can be compressed in 7.5 gigabytes using gzip. And the classical implementation of the suffix tree, it's around 600 gigabytes, and we need something smaller, of course. So in 2007, the compressed suffix trees came along with full functionalities. And the idea is to use some other data structures like suffix array, inverse suffix array, and LCP array, and some other operations like range minimum queries, next smaller value, and previous smaller value on the LCP array to simulate all the functionality of the suffix tree. So on one human chromosome 19, we took the implementation of the compressed suffix tree from SDSL, and we were able to build the compressed suffix tree in 32 seconds using just 64 megabytes. This is the final size of the data structure, which is a bit smaller than 1.2 gigabytes, and we use 2.1 gigabyte of working memory. Then we tried to scale up to 512 chromosome 19. And well, the final data structure is small, is 28 gigabytes compared to the 600 gigabytes of the classical data structure. And it took 16 hours and 30 minutes, more or less, and 1 terabyte of working memory. So the final index is small, but the working memory does not scale very well. And to use an index, one must first build it. Okay. Now, what we did, we used the prefix-free parsing as a data structure. So I will tell you later what the prefix-free parsing is. And we simulate the suffix-tree functionalities using a slightly different set of operations than the one that I told you before. And we use random access to suffix array, inverse suffix array, and the text. And we combine the operation of longest common extension plus the suffix array query to simulate the LCP and the range minimum query on the LCP. And we implemented other two operations called prev and next to simulate the previous smaller value and next smaller value on the LCP array. We tested on 1 human chromosome 19, and the final size of the data structure is not very good because it's 1.6 gigabyte, and we took like 1 minute to be built. We tried to index 512 human chromosome 19. Well, now the data size of the data structure is much better because it's 19 gigabytes. It's smaller than the SDSL1. It took only 30 minutes to build the suffix tree, and it took just 27.5 gigabytes of working memory, which is quite good. So we did some experiments on a 40-core machine with 756 gigabytes of RAM, and we tested our approach against SDSL, the compressed suffix tree, and the block tree compressed suffix tree. So here you can see the running time for the construction of the compressed suffix tree. So we are the yellow one, the orange one, and we are pretty fast. So SDSL scale almost linearly, as well as the block tree suffix tree, while our construction time scale quite logarithmically. So this scale is logarithmic scale. So we are pretty fast, and also we were able to build the data structure for 1,000 copies of the chromosome 19, not just 512. And for the memory construction, so the final size for SDSL and the block tree, compressed suffix tree, is almost always smaller than ours. But eventually we will become smaller than SDSL. But the interesting part is about the working memory. So the gap between the working memory of our solution compared to the gap between the working memory and the final size of the structure of the SDSL is much smaller on our solution. And this is why we managed to build the compressed suffix tree for 1,000 copies of chromosome 19. We also tested on 10,000 salmonella genomes. The results are in the paper that we published in at RNX this year. And the trend are very similar on both the running time and the memory construction. Okay, so how we did that? We used the prefix-free parsing, which is a pre-processing step that was used to build the BWT for very large data set. So the idea is that here we have our text. So we considered the text S to be cyclic, and we append W copies of a special character dash at the end. Now, we take a set of strings of length W, which are called trigger strings, and we go along the text and we mark all the occurrences of those strings in the text. So now in practice, we don't choose a set of strings. We just use a rolling hash and we mark all the position in which this rolling hash modulo some other parameter becomes equal to 0. So now what we do is we parse the text as this way. So we first extract the phrases, and a phrase is defined as follows. So a phrase starts at the beginning of a trigger string and ends at the end of the next trigger string. So we have that those phrases overlaps by W characters between two consecutive phrases. We take all those phrases, we put them all together in a dictionary, and we sort them lexicographically. And now we assign to each phrase a meta character, which is the lexicographic rank of this phrase in the dictionary. Now, the important thing is that the set of the phrase is prefix-free. This is why it's called prefix-free parsing, which means that no phrase is a prefix of any other phrase in this set. And this is important because this property is used to build the BWT, but now we will use it for our operations. So, as I told you before, now we are not using the prefix-free parsing as a preprocessing step, but as a data structure. So we want, as I told you before, simulate the suffix-free functionalities via random access to suffix array, inverse suffix array, and the string. We want to use the longest common extension operation, which we have two positions in the text, and we want to find the longest common prefix between those two suffixes of the text. So given the LCE operation and the suffix array operation, we can simulate random access to the LCP array, and we can compute the smallest values in one LCP interval using the LCE. And then we also implement two other operations, which is previous IH and next IH, which is the closest position preceding and following I with LCP smaller than H. So given a position I in the LCP, we want to find the previous and the next position smaller than H. So we need to implement some primitives, which are those ones, to implement the suffix-free functionality. And we need a set of data structures on the prefix-free parsing, built on the prefix-free parsing. I am not going to explain all of them because I don't have time. I will try to show you how to do an LCE operation and random access on the suffix array. The inverse suffix array is basically the same operation. So let's start with the LCE. So we have our text. We first consider here the lexicographically sorted phrases of the suffixes of D. So the suffixes are the one in black, and the gray part here is just to remember from which phrase this suffix comes from. And we have an LCP array here. We also consider the lexicographically sorted suffixes of the parsed. And we have a special LCP array. So this is an LCP array, but the longest common prefix is counted in characters. So this suffix corresponds to a suffix of the text. So we just compute the longest common prefix in characters. Now, let's say that we want to compute the longest common extension between those two positions in the text. So what we do, we first use the parse to find the occurrence of this character into the corresponding phrase in the dictionary. And the same for this position. And now what we can do, we can look for those two suffixes in the lexicographically sorted phrases of the suffixes of D, and we can use the LCP array to compute the longest common prefix between those two suffixes. Now, if the longest common prefix between those two suffixes is smaller than the length of the suffix, then we are done. In this case, this LCP value is equal. So what does it mean? It means that the longest common prefix may extend after these phrases. So what we can do, we can find the next phrase in the parse. So those are two suffixes of the parse. So we can find them in the lexicographically sorted suffixes of P, and we can query the SLCP array here, which tells us that their longest common prefix is 8. And then we need to remove W characters, value W. Why? Because we are counting AC twice. Because we are counting AC here, but we are also counting AC here as a prefix of D2 and D2. Okay? So LCE queries are done. And the LCE. Now, how can we do suffix array operations? So let's first consider the lexicographically sorted suffixes of the string. Now, the first observation is that each suffix of the string starts with a proper phrase suffix of length at least W. So each of these suffixes start with a proper phrase suffix of length at least W. And here in red, I've marked all those proper phrase suffixes. Now, the first thing that we do, we build a bit vector, which for some other reason is called BBWT. And the property, and this bit vector marks the first occurrence of this proper phrase suffix. So this is the first occurrence of the proper phrase suffix T dash. This is the first occurrence of the proper phrase suffix TAC. This is the second one. So what does it mean? It means that a rank of this bit vector up to this position tells me which is the lexicographic rank of this proper phrase suffix. Okay, we will use it later. Now, second observation. So here we have our lexicographic sorted suffixes of S. Now, we also consider the lexicographic sorted suffixes of P. And we can observe that the relative order of the suffixes of S, starting with the same proper phrase suffix, is given by the relative order of the corresponding suffixes of P. So if we consider those two suffixes, then we can see that their relative order is given by those two suffixes of P, which are the suffixes starting after the phrase that contains those two suffixes. Okay, are those two suffixes here. And their relative order is preserved in the order of the suffixes of P. And again, this is equivalent to find the relative order in the BWT of the parts. And we just need to find to the phrase identifier that contains this suffix. Okay, and the relative order gives us the relative order of the two suffixes of the string. So we want to find the relative order of the occurrences in the BWT of the parts of the phrases with the same proper phrase suffix. So how we do that? We build a grid in which on the columns we have the BWT of the parts, and on the rows we have the colexicographically sorted phrases of the dictionary. Why? Because here you see that two phrases which has the same suffix are grouped together. So we can find the relative order of the occurrences of the BWT of P in this box. All the points in this box, reading from left to right, gives us the correct order. So how we do the suffix array operation? So let's say that we want to find the suffix array entry at this position. We first use the BBWT to compute the lexicographic rank of the proper phrase suffix of length at least W. And this gives us this interval here because we pre-computed them. And those are just the number of ones in this BWT number. Okay. And now we know that this is the second suffix that starts with this proper phrase suffix. So it's the second point in this interval. So now we can take the phrase, this point starts, is D4. So we do an inverse suffix array of P query, and we find this position by just considering the length of this suffix, so the offset of this position within the phrase. Okay, we did some tests, and I have some time. Yes. Okay, we did some tests, performed some queries on our data structure. So not all the queries are fast as we would, mainly because of the way how the grid for the suffix array queries is implemented, which is a wavelet tree, which introduce a log p factor in the query time. But not all the queries, because some of the queries are on par with the other methods. And this is a full task in which we computed the matching statistics of a pattern. And we can see that the time is not so far from the time of SDSL in this case. But to use an index, one must first build it. And if we consider the construction time in the query time, and in particular in the full task, then we are faster than our competitors. And we build it. Thank you very much.
Thanks for the talk. Very nice. So we already have one question. It is slide number 5. For small inputs, the SDSL structure is smaller than the PFP structure, but uses more working memory to construct. Is it possible to transform from PFP to SDSL using small working memory?
Okay, this is a good question. So it's not immediate. I mean, we can use the prefix reparsing to build the information that is required to SDSL to build their data structure. So we can somehow be used as a buffer. But I don't know how much time would it take to implement all those things. I think that is possible. I'm not sure how much, if we can build all the informations that are necessary for SDSL to build their compressed suffix tree. Maybe the only problem would be if we need to build the shape of the tree. So this may be the only bottleneck that I can see in using the prefix reparsing to build the SDSL data structure.
Okay, thank you. Are there any more questions? Okay, so since there are no more questions, we can thank again Massimiliano for the talk.
And thank you for the organization.
Thank you very much. And I think it's time to greet everybody. And so I'm inviting Paola and Yuri on stage. Yuri. And we want to thank also Raffaella Rizzi, that is not able to join us now, but she's been very precious and important in the organization of this conference. I want to thank especially Yuri, that has managed all technical aspects of the conference.
So many issues
in this, and I think that Paola can...
Okay, let me thank everybody for attending the meeting first, and thanks to all the speakers for the nice talks and very interesting talks. Let me thank, of course, the steering committee of DSB for giving us the opportunity to organize DSB Milan. We are sorry not to be here in Milan and have the opportunity to visit the city, but there will be a next time. Of course, I want to thank Gianluca and Yuri for the efforts and Raffaella that mainly work in the backstage. Okay, I hope you enjoyed the meeting, and in any case, okay, there is somebody raising the hand. I don't know if somebody wants to speak or say something. Gianluca, somebody raised. I don't know. Anyway.
I can see. And then I want to also thank Simone Cicolella, that even though he's not one of the former organizers, but he has helped us a lot in managing the conference, the workshop. And
so it was a nice pleasure, and hope to you soon in Milan. In any case, you still stay in the Airmeet platform and discuss on the tables, near the tables. You will drink coffees and chat around. Okay, just to let you know, I just learned that now it's very easy to visit the Last Supper. So it seems that during this time, it will be easier next month to visit Last Supper, which is a touristic attraction in Milan, and let's hope to have a visit soon for all of you. Thanks again. It was really a pleasure for us.
Thank you very much to all the speakers. Please stay as long as you want.
Thanks, everyone. And goodbye, everybody.
Bye-bye.